So firstly, thank you for having me. Thank you for inviting me. Nicole, Leah, Chris, this has been an amazing conference. I've been amazed by the location and all of the guests and all the talks we've been having, so thank you. So I'm Patrick Hamann. As Jen mentioned, you can get me on Twitter there. And I'm here to talk to you today about CSS and the critical path. Now, what does that mean? I don't really know. I hope you'll know what that means by the end of this talk. So as Jen mentioned, it's a talk. It's really a bit of a ruse. I'm here at CSSConf, but I'm actually here not really to talk to you about CSS, but more about performance and the importance, but importantly how CSS is intertwined and tightly coupled with our critical path, the path from which a browser takes to render to our screen. So if you haven't guessed already, I work for The Guardian. It's a national UK newspaper, which is now an international media organization. We have offices in New York, Australia, and London. And I work on the core web team there, which we're helping to make the next generation of the Guardian website. We've spent the last 18 months completely re-engineering from scratch the Guardian website. It used to be before a horrible, large Java monolithic application, and we're now moving to a mobile-first responsive website. As Brad Frost once coined the phrase, planting the responsive seed, it's very hard for large organizations to shift to responsive. So actually, we kind of tiptoed along the way. We first replace our m.subdomain with a responsive site, which is going to become the platform and the basis to take eventually, hopefully this summer, we're going to completely remove the old site and have one single platform. And so today I'm going to talk to you about some of the lessons I've learned building this. Last month, we broke a record at The Guardian. We had 100 million unique users within the first month. That makes us now one of the largest news organizations in the world. But on the flip side of that, those 100 million are being made up of accessing our site from over 6,000 different devices. And our current platform, the old site that's there for 10 years, wasn't designed, it can't cater for this array of devices. And it's just not acceptable what we are serving to these devices, and we had to do something about that. But more importantly, the site is extremely slow. So here you'll see on the left-hand side our old site and the right-hand side our new site, and the difference in the rendering speed between the two of them. Just see have what you think yourself. So within 3 seconds, we've finished painting and rendering and fully completed loading of the whole site, whilst we're still chugging along on the old site. And that's a median average. It takes 12 seconds to paint and finish loading of our website to the user. Now, I just don't think that's acceptable, and I hope you guys don't too. But it's not just us at The Guardian to see this problem. User load time expectations, us as users, our expectation of how fast a website takes to render is reducing. From 2000, it was 9 seconds, all the way until 2012, it's just 2 seconds that your users expect your website to load in. And again, the problem's not just ours. This is taken from httparchive.org, a great Google initiative that they index data from the top 200,000 websites. And I ran this query on BigQueries last month to ask it, hey, what is the speed index? i.e., the speed index is a metric that is in milliseconds how fast your site takes to fully render. And the top 10,000 websites, the median average is 9,000 milliseconds, right? 9 seconds. Whereas we know that our users want it to load in under 2. Can you see where I'm going here with this? So, but The Guardian, how we have to relate this back to our business. So when we were starting out on the new project, we surveyed 3,000 of our users and asked them about 17 core KPIs, product indicators, of which one of them was speed. And unsurprisingly to me, those users rated speed as a feature the second most important thing, only after easy-to-find content. You'd hope on a news website that the content is easy to find. Although that did surprise the business, though. But it was great for me because that allowed us a leverage to really drill into them that we need to make this new platform fast. And it's not just that as well. There's been a lot of HCI research recently that has gone into the fact of the cognitive levels of us as users, how we perceive speed on machines. This is taken from Ilya Grigorik, high-performance browser networking. He works on the Google Make the Web Faster team. I strongly advise you read that book. But here it says that for us as users, to feel that a machine is actually functioning and working, any action you perform must respond within 1,000 milliseconds. 1,000 milliseconds. And that's not just, you can't just relate that to websites, you can relate that at home. I'm sitting on the couch, I'm watching TV, I change the TV channel. I want that TV needs to respond within 1,000 milliseconds for me to deem the machine working. And after 10 seconds, my mental subconscious just moves on, and that task is completely abandoned. So Tim Cowdeck's been talking about this a lot recently. So now we know that 1,000 milliseconds is what we're trying to reach. Our website should render within 1,000 milliseconds. What if we were to set a budget to enforce that in our development workflow? Every new feature, every new page we make has to hit that budget. So that's exactly what we did at The Guardian. We've set ourselves a budget of ensuring that all pages render within 1,000 milliseconds. No longer we can think in seconds as web developers. We really need to start thinking in milliseconds. So let's dive a little bit deeper into this. For us to be able to understand how we can paint within 1,000 milliseconds, we need to understand what's going on behind the scenes, how the browser goes from that, and you clicking on that link to being able to paint on the screen. But also knowing how the browser works makes us as web developers make better decisions when we build our web applications. So hopefully you've all seen one of these before. This is a waterfall chart taken from Web Page Test. There's a segment explaining the network. Each bit of the network is made up of the DNS lookup, so converting the nice theguardian.com string into an IP address. We then can go, the computer can use that IP address to go and make a TCP socket connection, a three-way handshake, and then finally I can make the actual HTTP request. I can say, hey, give me index.html. And when the server deals with that, it responds, and finally we can download the content. And so all of that has to happen before we can even start creating a DOM. But out of our 1,000 millisecond barrier, 600 milliseconds of that, on average, is already taken up. This is on a average 3G mobile connection. 600 of that is already taken up by latency. We've heard this before. Latency is the biggest killer to performance, and especially on mobile. So every network request you make, you're incurring this 600 milliseconds. And so that leaves us with only 400 milliseconds to really paint to the screen. And now you start to think of how important it is to rendering. So this is being very simplified, but this is what the critical rendering path is. This is what your browser has to go through to be able to paint to the screen. So let's look a bit deeper in that. So I ask for my index page. I perform the network on it, incur the 600 milliseconds. Once I've got the HTML, fortunately, I can start parsing the HTML and creating a DOM structure. Now, one of the greatest things about the HTML spec is that a DOM construction and HTML parsing can happen incrementally. So we don't have to wait for the whole file to be downloaded. We can actually start creating the DOM as the packets come in. And this is an amazing feature. So I'm sitting there, the packets come in, I'm constructing a DOM, and boom, my browser hits a script or a link element. It has to stop. It can't construct the DOM anymore. It has to stop blocking. It has to go back and perform the networking to go and get that CSS file. So I download the CSS file to create the CSS object model. Now, the CSS object model and the DOM together create a render tree. It's another tree-like structure that has all of the information about the nodes on your page from the top left to bottom right. But due to the cascading nature of CSS, we can't parse the CSS incrementally like we did with the HTML file because of the cascade. So styles at the top of the page might be overwritten further down in a media query or something like that. And that would actually constantly start painting and flashing to the screen and causing reflows. So, actually be a negative user experience. So we have to wait for the whole CSS file to be downloaded before we can construct the CSS object model. And then our lovely friend and foe, JavaScript. Now, if we find a script element, JavaScript blocks DOM construction because of that great feature, document.write. JavaScript can alter the DOM. And so because of that, the DOM can't continue to pass. But JavaScript is tightly coupled with CSS because it has to block and wait for the CSS object model to be created because what if JavaScript was to query a style on a node? And this is why the age-old best practice of putting JavaScript to the bottom, or even more importantly, declaring it as async, you're making a promise with the browser saying, I know this JavaScript is not going to do anything dodgy. You can just take it off the critical path. But it's really interesting, this relationship. It's intertwined, tightly coupled. And I ask this in interview quite a lot to people I'm interviewing. So I put JavaScript to the bottom of the page. Why do you put JavaScript to the bottom? Oh, because it blocks. Why does it block? and they never know. It's surprising how many people don't actually know what is the actual reason why JavaScript blocks our browser rendering. So we've done the good thing, we've taken JavaScript off. The only thing we're left with is the CSS object model. We need that. And so finally, we can then perform layout and paint. And you can see here how this is all traditional websites look like this. We've got our HTML, we then download our CSS and our JavaScript. If we make the JavaScript asynchronous, take it off the critical path, now we've already shaved off a lot of milliseconds there to be able to paint. So we know we have to get the CSS down as soon as possible. It should be the only thing on your critical path. And in my opinion, it is the critical path. But how can we optimize our CSS for this? Start to ask that question, what actually is your critical CSS? And especially on a responsive website, you know, that concept of above the fold no longer exists. Something that is above the fold on a mobile might not be above the fold on your desktop. So here's an average Guardian article page. Is my critical CSS the sharing widget, or the popular content, or the comments? None of this. It's only the article. The user came there to read the news. That is the only critical CSS that you require to paint to that screen. And it should be the only thing. So we take that one step further at The Guardian that, you know, we actually Ajax in and progressively enhance all the rest. So the initial payload actually only has the HTML for the article in it. This is our critical CSS versus our non-critical. And so Angelina, just up before me, had started to allude to this fact of, so we now know what our critical CSS is. But what if we were to inline that CSS into the head of the document? Knowing what we just learned from browser rendering, then the browser has everything it needs to be able to create the render tree within one HTTP request. Everything. We don't need to incur that 600 milliseconds again to go and download the rest of the CSS file. All of our styles, the critical ones for above the fold content, are delivered in the first payload. Now, I know it's very controversial, but that's exactly what we've started to do at The Guardian. So we've got the style element at the top. This goes against everything we've been taught as good web developers, you know. Separation of concerns, styles in CSS, behavior in JavaScript files, and completely separate. But if you want your page to paint within 1,000 milliseconds, this is what you have to do. So if you go to the Guardian beta site right now, you'll find this disgustingly ugly blob of JavaScript at the top, compressed into 14K. So if you've got a full TCP connection window open, you'll have enough information within the first packet for the browser to render to the screen. So that's enough of that. What is that actually like to the user? So the top doesn't have any inline, the bottom does. We've rendered in 600 milliseconds there. And we've basically nearly finished painting, and the one without hasn't even started. But for the observant ones of you in the audience would have noticed that I still have to load the rest of them, right? I've got my critical styles, but I need to be able to load the rest of them in. And so we now, at the bottom of the page, we have to async in the JavaScript and then create a style element and inject it into the head. Therefore, completely taking the rest of those styles off the critical path. Even more observant in the audience, we started thinking about that. But hang on a second, if you do async in the rest of your global styles, isn't that going to cause a massive, ugly reflow or repaint once those new styles come in? And you're, in fact, correct. That's exactly what happens. And once we first implemented this, a week later, the creative director of The Guardian came walking in and said, what the hell is this ugly flash on my website? And he was right. You know, it wasn't acceptable that the users was, yes, we managed to, if we optimize it well enough, you know, they wouldn't see it. But if they started scrolling soon enough, they'd see that horrible paint instantly. So the only way to get around this is that we obviously have to manage that somehow. We have to cache it. And so we looked to local storage to act as a cache. That what if we could, once we've asynced all of that CSS in, we could then cache it in the user's local storage, and then next time round, we have all of the information within the first request to be able to paint to the screen, avoiding any flash of on-site content. So first, we ask if the browser is modern enough. The BBC's cut the mustard test. You know, does it have XHTML, HTTP object? Does it have event listener? If not, no, just use a normal odd link. But Is there already styles in local storage? Yes, great, let's paint. If not, do they have local storage space? Now, this is an interesting one. We found that a large percentage, and especially iPhone users, have a quota exceeded already on their local storage. If so, request it with Ajax, cache it in the local storage, and then paint again. And then on the next time round, we can instantly just go straight to instant painting with all of our styles, not making a single request to a style sheet. So here, we've just onto our top, back in the head. We now check to see if the storage item is there. If it is, inject it into a style node there instantly. All of your styles within the first HTTP request, and enough to deliver the news to the user within 1,000 milliseconds. Again, now down the bottom, so we've done our normal Ajaxing, but we now have to store it. So here, we're actually doing a bit of caching validation for free at the same time here. If they've managed to get into this block, it means that either their style is outdated or they don't have any. So we first loop through all of the local storage items to check if they match against our pattern. If they do, we clear it, and then load in the new one and store it again. So we're using an MD5 hash here of the file. So every time we practice continuous delivery, we're deploying about 4 or 5 times a day now. And so instantly we can invalidate that CSS, the old global CSS, and get the new ones straight away. But what does this mean actually, again, to our users? So here, we're using web page test here. This is a UK cable connection. And so before, we're still blocking rendering, waiting for all of our CSS and our JavaScript to download. We async the JavaScript, and then we inline the CSS and cache it in local storage. Instantly look at the difference to the waterfall here. We've got a start render event right there, even though we're asyncing in the rest. The browser doesn't need it because it's got its inline styles here. And we've managed to shave over 500 milliseconds off our start render event just by inlining the CSS and caching in local storage, breaking our 1,000 millisecond barrier. So again, if you go and look at the site now, you'll notice that in the style sheet tab in any inspector, you won't see any physical files downloaded. But if you go and check the local storage, you've got your CSS right there. Interestingly, we also do the same with our fonts to avoid any flash of unstyled text with the font loading. Now, as well as having fast pages, this also creates a much more resilient system. A system in which I'm traveling on the train, a friend of mine shares a link to a cool article on Twitter, I click on it, but boom, I go into a tunnel. Now, fortunately, my mobile had enough networking to perform the network request, that first HTML request. But normally, I'd go into the tunnel, and then it would find the CSS file and try and make the downloading for that. But you can't, because you're in the tunnel. And that's that big, white, blank screen that we're all so familiar about. With this technique, we've created a system resilient to failure that I only need to make that one request, and I have all of the information. Google, to do this, Google and Bing have also do this. You know, it's why I rate one of Google's search results pages the fastest page in the world. What they do is actually, more interestingly, send down all of the styles in the first request. And then they put it in local storage, but they set a cookie so that when you request it again, all the subsequent requests after that have already got all of the styles. We can't actually do that at Guardian because we keep a completely stateless domain, so we don't use any cookies so that we can cache our HTML on. So with all performance techniques, you must monitor these and optimize and repeat. So to do this, I built a grunt task that in the CI, now I'm monitoring the size of those head files. And so whenever a developer updates the size of those files, I can get alerted to see if it goes too big. Because obviously, we don't want to go in the negative opposite way, that the file gets too big and then we're actually bloating our pages and slowing them down. So in the CI, we monitor these. And I now know the raw and the gzip file size, and it gives me, and I can trend this over time and set a threshold alert, knowing when our assets get too big. Again, in pull requests, this is a big code smell to me when someone's adding something to the head file. You have to ask them, is that your critical CSS? Does that feature really deem to be in the head? And so monitoring assets like that is all well and good, but actually what are real users seeing, and especially across the world? And so to do this, we use a tool called Speed Curve, and this uses clusters of web page test instances around the world and we can, it tracks and trends analysis for us, and I can filter this by our start render event or our speed index. And I instantly know how our page is performing over the last 2 weeks. But more importantly, again, I can set thresholds on this and compare my sense against our own competitor, which is our old site, or even our competitors, business competitors in the wild. If you have tools like this, it's really, really important that you then spread this around the department. So now every week, all of our, everyone in our department, from our project managers to our designers, get this report telling us how fast the website is and if we've broken anything. And this is really, really important. Making everyone in the team accountable for performance is the only way that you can ensure that you maintain that. And it's been really interesting having project managers come up to us and say, hey, what happened last week? Why have we slowed down by 100 milliseconds? And it's great to see them actually caring about that, getting everyone involved. Now, I've talked a lot about our technique, but what are some of the alternatives out there? Google PageSpeed module for Apache or Nginx has a feature to be able to inline on the fly. So they actually render the page, work out what the inline styles are, and inject them into your page. So this is at a proxy level. So you can sit this Nginx proxy in front of your systems. Now, there's reasons why I love PageSpeed. It does a lot of good optimizations, but the specific inlining of CSS feature, there's some reasons why I don't like it. I like to have a lot more fine, granular control over what's going in the head or not. UnCSS and grunt UnCSS task by Adios Mani. This, you can pass it in multiple files on your website, and it will actually work out what is the CSS required for this. Nicole earlier on mentioned that she did all this great work to optimize a CSS file, but it was actually Bootstrap in the end that was weighing up 50%. With this as a post-optimization, her worries were she doesn't want to delete some of Bootstrap because it would make upgrading in the future. If you have this as a post-optimization, you can get it to strip out your CSS file and you just have a new minified one that only has the bits of Bootstrap in it that you are using across your core templates. Basket.js, again by Adios Mani. This uses exactly the same pattern of using local storage as a cache management and invalidation layer. But all of this seems like a hack. We shouldn't be having to do this as developers. Take these extreme things of breaking everything that we've learned to be able to get that last couple of milliseconds out of our performance. Fortunately, there's been a lot of thinking around this area recently. So HTTP2, which is the HTTP, the underlying transfer protocol layer of the web, we're actually currently on 1.1 that was spec'd in 1997. It's now 2014, and we finally got a new point, a major version. This is actually near to finishing of the standard. It will be finished by the end of this year. But how does this relate back to what I've mentioned is there's a great feature in it called server push. Now, HTTP2, the biggest benefit to us, and as we know, latency is the biggest killer. How do we reduce those round trips and the latency is that you can have multiple bidirectional messages on the same TCP connection. So for my HTML file, my CSS file, and my JavaScript file, I don't have to open up 3 different TCP connections. I can send them all down concurrently down the same socket. But we've got this traditional flow, right? We ask for the HTML file, the server gives it back. Your browser then parses the HTML, finds the CSS file, and then goes and requests it again. But as web developers, we know that the browser is about to then request the CSS file or your core JavaScript file. So knowing those decisions, what if we could push them down with the initial HTTP request? So this is a new feature called server push that completely forgets the need of any of our techniques here, because I can say, hey, browser, when you ask for the initial HTML file, you can say, hey, and here's all of my other core assets. I know you're going to need them. And let the browser do the cache invalidation or work out if it needs them or not. Service workers. Now, this, to me, HTTP2 and service worker are among one of the most important features coming to the standards that we're going to have within these next 5 to 10 years. Service worker is being worked on by Alice Russell from the Chrome team and Jake Archibald, and they're actually, interestingly, really developing the whole spec out in the open on GitHub. I strongly advise you to go and check it out. But so service worker is a request handling with a persistent cache. So you can create a worker level that handles all of the requests within your browser and just deem whether or not you want to go back to the network or return something from a cache. So basically, it's app cache on steroids, or the better app cache. And so here's the traditional model again. I request my CSS file, and then we go off to the server to go and get it. But what if the service worker already had one in its cache? Or, we were using local storage, abusing local storage for this pattern. Now, we actually have a new cache object in CSS, and service workers that have the native new promises spec built in. It said, right, if I've got that in my cache object, return it. And so now we don't have to ever even talk to the server. Again, having all of the information, the CSS, to be able to paint within our 1,000 milliseconds. So, just to summarize, I've actually gone really, really fast. Here are some of the things that I've learned along the way and that I hope you do take away from this. Please have a think about inlining your critical CSS and deferring all non-critical assets. Your critical rendering path is the most important thing to getting your content in front of your users. And anything you put in front of it is going to block them. And as we know, that 600 millisecond round trip for every request is just bolting on to your millisecond budget. Where possible, always cache aggressively, and maybe in local storage, or hopefully in the future in service worker, and set a performance budget on your sites. But once you've got that, you need to always measure, optimize, and repeat. Our websites get slow on a day-by-day basis as we add features to them. You need to constantly be measuring that. Or thinking about, when I add a new feature, do we actually need this feature? Or how can I better optimize this feature, make it fast before we include it? Or is this feature going to detriment our loading or the performance of other features? But most importantly, feature performance is a requirement. It's not a feature. You can't retrofit it. You can't, oh, don't worry, the ops team are going to handle it. We all, as web developers, must be worrying about this. And as I said before, the more you make this information available to the rest of your business, the more the rest of your business will start caring. Thank you.